This is an axial flux motor that I spent about a week making, and it works pretty well. With a radial flux motor, you have like a cylinder rotating around a cylinder because it's radial, but with an axial flux motor, it's kind of like a disc spinning around a disc. So you can see in this axial flux motor, once I put the rotor on, the rotor part with the magnets, stator part with the coils, I put this on, you can see it's a disc spinning on top of a disc. The first design decision I had to make was how many slots and magnet poles that I wanted. I ended up opting for 9 slots and 12 magnet poles, which means 12 magnets and 9 coils, because the less coils I would have to do, the easier it would be to make the motor. There's 2 important numbers to look at when you're trying to figure out your slots and your poles, and that's the cogging steps and the winding factor. The winding factor is pretty much how efficient your winding is going to be at generating a magnetic field, and the cogging steps is kind of like how it clicks to the next step, and you can see that in this clip. So a higher cogging step factor would mean it would be smoother. Mine is pretty low, so it's not terribly smooth. I catted this motor in one sitting, so here's the design. If you want to learn more about it, I wrote an instructable about it on the description and how you can make your own, and also a 3D printed version. I started by machining the center shaft on the CNC mill so that I can get that pattern of 6 at the top, and then I was like, oh, I'm going to bring it over to the lathe so that I can do the bearing, the press fits for the bearing, and then I realized something. I just realized the part is not concentric at all. Since I eyeballed the centering, the part is not concentric at all. So I can't actually use the lathe for this job. I have to just like hit it with the file. So the wobble that you're seeing is a result of the shaft not being concentric to the rest of the stock, which I'm holding with the lathe. That's pretty bad because I can't actually use the lathe to do the bearing press fit job. So instead, I just rubbed a file against it with the lathe until I eventually was able to get the bearing to press fit on. And it wasn't really a good press fit, but I used this thing later called green Loctite to kind of glue it in. After I cleaned it up on the lathe, I brought it over to the tapping handle so I could tap each of the holes in the shaft. I forgot to mention this earlier, but when I was drilling out the holes, I broke a drill bit inside of one of the parts of the shaft. I didn't feel like remaking it, so I'm just going to have 5 tapped holes instead of 6. After finishing the central shaft, I went ahead and started machining the rotor on the CNC machine. This is a desktop CNC mill, so it's not dangerous enough to need a shop buddy, so it was a little bit more convenient for me to use. The rotor, you'll notice, has 2 indents. One is for the shaft, so the shaft can kind of slot a little bit more in, which should hopefully allow it to sit better inside the rotor and be more concentric. And the other indent is for the back iron to go to, which is going to be a disc of steel, which the job of the disc of steel is to align the flux of the neodymium magnets. So I get a little bit more performance out of it with a back iron. I really like Greenhill Forge's explanation on what a back iron does, and I'll also leave a link to his video in the description, but I'll leave it to him to explain this concept.
If we make the rotor out of a steel disc, it'll act as a back iron. A back iron provides a low reluctance path for the magnetic flux to complete the magnetic circuit, which channels and concentrates the magnetic field on the opposite side.
Something that Greenhill Forge doesn't mention is that some steels are better at achieving this than other steels. For example, I'm using silicone steel here, which is twice as good at achieving this effect than traditional mild steel. I cut up the steel disc on the metal laser cutter that my school has, and then I went ahead and epoxied the disc into the aluminum rotor. I wanted the rotor in general to be aluminum for heat dissipation a little bit, and also so that it's lighter. I epoxied it in with high heat JB Weld, since these motors get really hot and I didn't want anything to come apart. After epoxying the back iron in, I started epoxying the magnets in. The little black piece is a jig to help me epoxy in the magnets a little better. It's very important to have an alternating polarity, so it goes north-south, north-south. This is important for the motor to actually be able to spin at the end of the day. You might notice that I'm using 2 magnets here instead of 1 magnet. This is because it's kind of hard to get magnets that are triangular shaped for making like motors and stuff. So I'm using 2 magnets to get roughly a triangular shape, because the closer I am to a triangle, the better it is at covering the entire surface area with magnetic fields. After machining the rotor, I started machining the stator. Here I'm using a 3D printed jig to help me wind the coils, and since I'm only winding 9 of these, I'm just doing them all by hand. One thing I have to do is crimp them a little bit to get them to fit, and I'm using 8 turns of 14 gauge magnet wire. Something to note is that I'm not using round magnet wire, but I'm using square magnet wire, so I get a little bit of a better fill factor, which means that the coils end up being a little bit more efficient than if I was using round magnet wire. After I've done about 9 of these, I go through and sand down the enamel on the magnet wire so that I can eventually later solder them all together. Remember this from earlier? This is the winding scheme, and it will tell us exactly how to solder up the motor. All of these wires need to have a high and a low, so that means they need to be wound the same way. All of my coils are wound counterclockwise, so I could just look at this and track which one's the high and which one's the low and solder it up that way. I'm going to be soldering up in a Y configuration. There's 2 ways to solder up brushless motors, since it's Y or delta. It's not too important which one you pick because it will spin either way, but a Y configuration traditionally has more torque than the delta configuration. For the Y configuration, you just solder it by making sure to connect all of your end terminals together so that they all terminate together. So this is your Y endpoint, and then your start points are where your 3-phase input comes from. So for example, if I wanted to run this motor, I would hook up these 3 on the right to a speed controller and hook up these 3 at the end to each other. I went ahead and hooked up the motor to an oscilloscope to see if the wiring was right, and I spun it by hand, and using the fact that all motors are generators, I was able to see that I was generating an electric field. So it worked, and I was able to move on to the next step. I went ahead and connected the motor to a hobby grade speed controller, and as you can see, it did not work. No. After a bit of finagling with the hobby grade speed controller, I realized it wasn't going to work. So I swapped over to a VESC, and that got it to spin.
Oh, yo, yeah, it's spinning. Oh my god. Jesus. Wow. This should be good. You can try it again. If this doesn't work, I'll swing it back. Oh.
So at this point, we were testing without any steel in the stator, and it wasn't really designed for there being no steel in the stator. You'll see why in a second.
Whoa, whoa, whoa. Fuck, Jesus Christ. What just happened?
After that happened, I realized it was time to put steel into the stator of the motor. And I'm going ahead and fabricating here in a very particular way, which I'll explain in a second. But the point of having the steel in the motor is that it amplifies the magnetic field of the coils. The way that adding steel helps is because there's something inside of steel called domains, and they're all kind of like just wobbling around and unaligned. But when you induce a magnetic field with, say, a coil, all these fields get aligned, and now the steel kind of acts as like a magnetic amplifier. The reason I'm using a bunch of layers of steel rather than one big chunk is to minimize eddy currents. Eddy currents are circulating loops of current induced in conductive metal, like the steel, when the magnetic field through it changes. And in motors, they waste energy as heat and create drag. So to minimize this, we break that field up by using stacks rather than one big chunk. After going through this process of laminating the steel, I go ahead and epoxy it into the stator of the motor. Another benefit of having the steel is that the rotor is now magnetized down to the stator, so I should be less concerned about the rotor popping out like it did earlier. And another thing I went ahead and did for myself was make this mounting plate so I can actually clamp it down to the table. With all that said and done, it runs pretty well.
Oh damn, it burns my finger. Oh my gosh. That's crazy.
One funny thing that I could do is run it and then use some sandpaper to clean off the top. So it's kind of like its own lathe. I mentioned I swapped over to a VESC earlier. The benefit of a VESC is that I have a lot more control over the parameters of the motor. So here's me playing around with the VESC tool software a little bit. The VESC tool also gave me the parameters of the motor and kind of tells me how much torque to output at a given current and how fast it would go at a given voltage. Alright, after all that, it was time for some actual testing. So I went ahead and 3D printed this little coupler and then strapped the Axial Flux Motor onto this dynamometer that my school had. And the dynamometer allows us to see things like torque and speed and the power that this machine can actually output. And knowing the electrical power and the mechanical power gives us efficiency as well. Alright, I'll go ahead and explain what we're seeing here. So, I have two measurement systems going on. The bottom right is the dynamometer that is giving us power in watts on the left. In the middle it is giving us ounce-inch as torque, and on the right it is giving us speed as RPM. So that was the dynamometer, which was mechanical, and I'm reading electrical off of the VESC. So I'm able to see this through my laptop, which is connected to the speed controller. The most important dial is the wattage, which is the top middle blue dial. And that allows us to compare that to the wattage off the dynamometer. So comparing electrical to mechanical power, we'll be able to get efficiency. And I'll show the graphs at the end. This behavior we're seeing right now is called cogging. It's because the dynamometer requires a little bit of torque and the motor isn't able to get over that until I turn it down with that little knob. So here I start increasing the amount of torque that the dynamometer is putting on the motor, and you can see that in the change in the middle number of the dynamometer, the red 16, 20-ish number now. I slowly increase the torque, and that increases the amount of power that the motor needs to draw. So I slowly increase the torque until eventually the motor gets weaker and weaker and stalls, and that gives me a good sense of the max power, the max torque of the motor. All the previous testing was done with pretty considerable speed limits and current limits. There's still a current limit because the VESC I'm using is just a random one that I found. It caps out about 70 amps. But I turned off the speed limit on it, so before it was capping at around 6,000-ish RPM, and now I'm able to run it at significantly higher than that. I would run it at more, but I'm not unfortunately able to because of the parameters of the VESC. And also spinning it super fast eventually made a magnet fly off, and you'll hear that in this clip. So I would need to go back and re-epoxy the rotor in, or sorry, the magnets in the rotor. As promised, here is the data. In the test with the current limit and the speed limit, I'm able to get to about 600 watts electrical power and 200 watts of mechanical power, giving me a peak efficiency of about 40%, which isn't great, but not awful for a hand-built motor. And in the test where I still have a current limit, because if I don't have a current limit, the motor blows up, but I have removed the speed limit, I'm able to get to roughly 900 watts electrical power and 200 watts mechanical power. So lower efficiency, about 25% efficiency there, but still not awful. Probably next steps for me is to test out doing things like increasing power by having a double rotor, or doing things like getting a bigger and better VESC. But yeah, all in all, I'm pretty happy with the outcome of this project. Yeah, that's it. Bye. Oh yeah, and please subscribe, please.